3A, Machine Learning for Computer Vision 5. My name is Vladlen Colton, and to my left is John Barron. And John will introduce the first speaker.
Hi, everyone. Our first talk today is StarGAN, Unified Generative Adversarial Networks for Multi-Domain Image-to-Image Translation. It's by Jun-Ye Choi, Minje Choi, Munyoung Kim, Jung-Woo Ha, Sunghun Kim, and Jaegul Choi, and Yunjey will be presenting. Thanks.
Thank you for introduction. Hello, everyone. I'm Yunjey Choi from Korea University. The paper I'm presenting is StarGAN, Unified Generative Adversarial Networks for Multi-Domain Image-to-Image Translation. This is a joint work with my colleagues, Minje Choi, Munyoung Kim, Jung-Woo Ha, Sunghun Kim, and Jaegul Choo. This work is about image-to-image translation, which is the task of converting images from the source domain to the target domain. Recently, many image-to-image translation frameworks have been proposed using the generative adversarial networks. For example, their models can convert grayscale to RGB images, horse to zebra, photo to emoji, and cat to tiger or lion. We extend the previous work into multi-domain image-to-image translation. For example, we can imagine an application that can change hair colors. In this case, each hair color represents one specific domain. To learn image translations between all hair colors with the previous work, we should first train a generator for mapping from blonde hair to brown hair. If the target domain has changed, we should train a new generator independently. Likewise, if the source domain has changed, we should train a new generator again. This shows that the previous work had limited scalability in handling multiple domains, since different models should be trained for every pair of image domains. To address this limitation, we propose a shared architecture for the generator. The idea is simple. Our generator takes in as inputs both an image and a target domain information. We use a label, for example, one hot vector, to represent domain information. And our generator learns to flexibly translate the input image into the corresponding target domain. By changing the target domain label, the generator can generate images with different hair colors. In this way, we can learn multi-domain image translation using a single generator. To summarize, previous work had limited scalability in handling multiple domains. To address this limitation, we propose a shared model that can handle multiple domains using a single generator. We named our model StarGAN since it has a star topology that connects multiple domains. Let's see StarGAN in more detail. First, input for the generator. The generator takes as inputs both an image and a target domain label. During training, we randomly generate our target domain label and train the generator to flexibly translate an input image into the corresponding target domain. We use an encoder-decoder architecture for the generator. Pink represents the encoder part and yellow represents the decoder part. First, we use 2 downsampling layers to compress the image resolution. Then we use 6 residual blocks to learn image translation. Lastly, we use 2 upsampling layers. So the translated image has exactly the same size as the input image. In this case, the resolution is 256 by 256. Now let's see objective functions of StarGAN. We adopt an adversarial list to make the translated image indistinguishable from real images. The discriminator learns to classify real images as real. And for fake images, the discriminator learns to classify them as fake. On the other hand, the generator learns to fool the discriminator so that the generated image is indistinguishable from real images. To generate images that are properly classified to the target domain, we add an auxiliary classifier on top of the discriminator and impose the domain classification laws. First, the discriminator learns to classify real images into its corresponding domain C'. This can be done by minimizing softmax cross-entropy loss with the original domain label. We assume that the input image and domain label pair is given by the training data. On the other hand, we impose the domain classification laws of fake images when optimizing the generator. By minimizing these classification laws, the generator learns to generate images that are properly classified to the target domain. by the discriminator. Note that the probability scores of the discriminator should be same as the target domain label, which is the input for the generator. However, minimizing the adversarial and domain classification loss does not guarantee that the translated image preserve the contents of the input image. For example, this image does not preserve the contents of the input image, but it can be classified as real and blown hair by the discriminator. To alleviate this problem, motivated by cycle gain and disco gain, we add a reconstruction list to the generator. We use the same generator again, but now inputs are the translated image and the original domain label. In this case, the original domain label represents black hair. Again, we assume that input image and domain label pair is given by the training data. And the generator tries to reconstruct the original image by minimizing these reconstruction lists. Now the output image should look like this. And by backpropagation, the generator learns to preserve the contents of the input image and change only the domain-related part. And let's take a look experimental result of StarGAN. First, we compare StarGAN to the baseline models on a facial attribute transfer task. We adopt diet, cycle gain, and IC GAN as our baseline models. We use the CELOP-A dataset, which provide attribute labels such as hair color, gender, and age. For the case of cross-domain models such as diet and cycle gain, we train the models multiple times for every pair of image domains. We also perform image translation on a multi-attribute transfer task. For the case of diet and cycle gain, we perform multi-step translation to synthesize multiple attributes. This qualitative result shows that StarGAN not only has scalability, but also provides higher visual quality of translation results compared to the baseline models. For quantitative evaluations, we conducted user studies using Imagine Mechanical Talk. The users were instructed to choose best translated image based on perceptual realism, quality of attribute transfer, and identity preservation. The choices were 4 randomly shuffled images generated from 4 different models. As you can see from the tables, most users selected StarGAN as the best model for both single and multi-attribute transfer tasks. One possible reason why StarGAN outperforms cross-domain models is the multitask learning effect. Instead of learning only a single translation, StarGAN learns multiple translations using a single model, so it can learn more about global features such as facial key points or hair position. We also test StarGAN on a facial expression synthesis, where the task is imposing a particular facial expression to one input image. For comparison with cross-domain models, we fixed input domain to a neutral expression, but target domain can be one of 7 different facial expressions. Only StarGAN clearly generate natural-looking expressions while properly maintaining the face identity of the input. We believe that the superiority of the StarGAN in image quality is due to its data augmentation effect. The facial expression dataset contains a relatively small size of samples. When trained on 2 different domains, diet and cycle GAN can only use 1,000 training images at a time. For example, 500 images for a neutral expression and another 500 images for an angry expression. On the other hand, StarGAN utilized 4,000 images from all the available domains for its training, so it can generate more natural-looking expressions. For a quantitative evaluation, we compute the classification error of a facial expression on synthesized images. We assume that if generator translate images well, then the translated images will be classified as the target expression. First, we pre-train a facial expression classifier using real images with facial expression labels. Then we use a pre-trained classifier and compute the classification error of the images synthesized by 4 different models. As can be seen in the table, StarGAN achieved the lowest classification error, indicating that the model produces the most realistic facial expression among all the methods compared. And the last column shows that the number of parameters required to train all translations for facial expression synthesized. Note that the source domain is neutral expression, but the target domain is one of 7 different facial expressions. So diet needs to train 7 different models, and CycleGAN needs to train 14 different models to learn mappings, both from source to target and target to source. On the other hand, StarGAN requires only a single model, regardless of the number of domains. Now let me show you some dynamic results and conclude this presentation. By using only a single generator, StarGAN can synthesize facial attributes. The odd columns show input images, and the even columns show translated image by StarGAN. And this is the result of facial expression synthesized. Let's see for a moment. You can check our PyTorch implementation from this link. And for any questions and more details about StarGAN, please stop by our poster E21. Thank you.
Please stay. If there are any questions, there's microphones here and here. Please line up. I have a question for you. In the meantime, I noticed the data set you train on tends to be mostly celebrities, like American celebrities wearing makeup. Right. Does the model have any data set bias issues, or does it generalize well to people who, say, aren't wearing makeup or aren't American celebrities?
Okay, so good question. So for Celeb A data set, the data set contains many Western images, so it does not work well Eastern face images. So, but in our cases, as you can see in these pictures, so at right bottom, there are some Kim Tae-hee, which is talent in Korea, but the translated image shows some changing, some brightness of images, and it works not well when there's some makeup images. Yeah.
Interesting. Yeah. Thanks. There are no, question over here.
Okay.
Yeah, so to follow up on this question, did you try more data sets which are a bit more different? I don't know, like not just faces, which may have a lot of common features. I don't know, bags, shoes, something like that.
So your question is, can we apply StarGAN other than face data set?
Yeah, so maybe data sets which are a little bit more different in terms of the features.
Okay, so actually we test StarGAN on a collection style transfer task. In collection style transfer, we define the domain as a collection of images of specific artists such as Van Gogh. But actually, I did not show the result in the presentation, but you can see the result in our poster session.
Okay, great. That's all the time we have for questions. Let's thank the speaker again.
Okay, thank you.
All the spotlight presenters, please come up and sit in the front row. There are seats allocated to you. We'd like you to be ready here when we start the spotlight part. Great. The next talk is going to be High-Resolution Image Synthesis and Semantic Manipulation with Conditional GANs by Ting-Chun Wang, Ming-Yu Liu, Jun-Yan Zhu, Andrew Tao, Yang Kautz, and Bryan Catanzaro. And Ting-Chun is going to give the talk.
Okay. Thank you for the introduction. The goal of this work is to do image-to-image translation. For example, given a semantic label map like this, our goal is to turn it into a realistic picture. Another application is to use user sketches of human faces or cats, and we want to turn them into realistic pictures too. So our work is based on GANs, generative adversarial networks. There are some prior work that use GANs to do image-to-image translation. However, the results are usually limited to low resolution and have artifacts at high resolution. Recently, there are some work that can synthesize high resolution 2K by 1K size images without using GANs. but their results usually lack fine details or realistic textures. In addition, some previous works also allow users to interactively change the results, but again, are often limited to low resolution. So we want to integrate this feature into our framework and also extend it to high resolution. To summarize, our work has made two major contributions. The first is we can synthesize high-resolution, realistic images. And the second is we allow users to interactively edit the results so they can get the exact image they want. Now let's see how we do this. Our work is derived from pix-to-pix, which is also based on GANs. Given input image, the generator will first translate it into a fake image. The fake image will be concatenated with the input image and put into a discriminator. The discriminator should be able to determine that it's fake. On the other hand, when a real image is used, the discriminator should be able to output real. Then, when we are training a generator, the generator should be able to follow the discriminator and make it output real. So our work has two differences from pix-to-pix. The first is that we extend to high-resolution image synthesis, and the second is we use instance-level segmentation to further improve the results. To extend to high resolution, we made three modifications to the generator, the discriminator, and the objective function. We have a coarse-to-fine generator, multi-scale discriminators, and a robust objective function. For our generator, we'll first downsample the input map, and the low-resolution input will be put into a series of residual blocks to output the low-resolution image. Then, the last layer of the feature of the low-resolution feature will be added to the high-resolution feature and put into another series of residual blocks to output the final image. For discriminators, we'll first build image pyramids for both the real and the synthesized images. Then different layers in the pyramids will be put into different discriminators to determine whether they are real or fake. This ensures that the image looks real both globally and locally. Finally, for objective function, previously, we only want the last layer of the discriminator to output real. Now, in addition to that, we also run a discriminator on the real image and try to match the intermediate representations for both pyramids. This can be seen as the learnable perceptual loss. To summarize, these three modifications enabled us to generalize to high-resolution image synthesis. Next, we adopt instance-level segmentation to further improve the results. We use it for two different purposes: to improve the object boundaries and to generate multimodal results. For boundary improvement, suppose you are given a label map like this. Using this map alone, it's very difficult to differentiate between different cars in the image. But if you are given an instance map like this, it becomes much easier. To utilize this map, we first extract the boundary map from it. Then, the instance map can be seen as the label map plus the boundary map. And these two are concatenated together to put into the network. This is an example showing the benefits of using instance maps. As you can see, using instance map helps to create images with clear boundaries. Finally, using instance map also allows us to generate multimodal results. So first, what does multimodal mean? Given the same input map, we can generate many different outputs. So all these four images are valid outputs for the same input map. To generate them, we use a feature embedded scheme. During training time, we'll first run a feature encoder on the original image and create a feature map. Then we run instance-wise average pooling on this feature map, which means for each instance in the image, we'll average its feature values. Then the average value will be broadcasted to the entire instance. We repeat this step for all the instances in the image. Then this feature map is concatenated with the label map and generates the final image. So this whole process is trained end-to-end So the feature map should be able to encode the appearances in the original image, like the color of the car or the texture of the road. Finally, during inference time, we can just change the feature map to create different outputs. Now let's look at some results. We compare with two state-of-the-art methods, Pix2Pix and CRN, and we run them on 5 different data sets. This is the quantitative comparison. So we run a semantic segmentation network on the results of different methods. As you can see, our results are much better than the other methods. We also compare to the Oracle results where the segmentation is run on the original images. Note that our results are pretty close to the Oracle result. Next, for a subjective user study, about 93% of the users prefer our results to Pix2Pix and 86% to CRNs. For qualitative comparison, we show side-by-side comparisons of different methods. We also scroll between the results by different methods so you can see the differences more clearly. So for the rest of examples, we only show the scrolling between CRN and our result. As you can see, our results contains more details like the car headlights in the image. So this is an example on the NYU dataset result. Note that Pix2Pix contains more artifacts and CRNs are usually more blurry. Here are some examples on the AD20K dataset. And finally, we show an edge-to-face example. So this is the input edge map, and this is the synthesized image. For your reference, this is the original image that was used to generate the edge map. We show a blending of the two images to convince you that they too have the same expression. Here's another example, the synthesized image and the original image. The synthesized image and the original image. And one last example here. Okay, so let's look at some applications. We build an interface for the users to interactively change the result. For example, change the texture style of the road. We can also change the lighting in the image. Or try to edit the eye shape or color, or even different makeup effects. We can also try to add eyebrows to the face, or add mustaches, or even beards. Okay. We can also directly edit the input label map to create different results. For example, change all the trees into buildings. We can also add a new object into the scene. For example, add a new car. And finally, the user can directly paint on the canvas to create different outputs. For example, paint more trees into the scene. Or try to make the eyes look bigger. Or even change the shape of the eye a little bit. So our work has also been used by others in unexpected ways. For example, Mario built an interesting face-to-painting application using our code. And last, we show extension to videos. Suppose you are given semantic label map video like this. So our method can be extended to video synthesis by incorporating a novel objective function and new network designs to ensure the temporal smoothness constraints are satisfied. Okay, so since the input is just some label maps, we can also just edit them to create different outputs. For example, we can try to change all the trees into buildings. We can even edit the styles of the buildings and the roads. Maybe just edit them again if you don't like them. Recall that the buildings are actually trees, so we can change them back to trees and edit the styles again. Okay, so to summarize, we present a GAN-based framework that can first synthesize high-resolution realistic images, and second, generate multimodal results. We thank the following people for their helpful comments and thank the two methods for sharing their code. Our code is online now. Thank you for your attention.
We have time for a quick question. If there is a question from the audience, please line up to the mic. In the meantime, I'm going to ask a quick question myself. So you've made a number of contributions that you highlighted in your talk. Which one do you think is the most important? Which one has the highest impact? Is it the generator architecture or the loss function or something else?
Yes, so we made a ablation study about different components in our network architectures and objective functions. So all three of them helped to increase the performance. Yeah, I think the generator architecture helped the most in terms of the numbers, but I'm not 100% sure on this. If people are interested, you can look into our paper and you should be able to find the results.
Okay. Yes, a quick question, please. So the question is, how much data does it need to train the GAN part?
So for the cityscape dataset, it contains 3,000 images for training. And I think for the phase dataset, it contains about 30,000 images.
Great. Let's thank the speaker again.
Our next talk is Semi-Parametric Image Synthesis by Xiaojuan, Qifeng Chen, Jia Jia, and Vladimir Colton. And Xiaojuan and Qifeng will be presenting.
Good afternoon, everyone. I'm Qifeng. This is a joint work by Xiaojuan, me, Jia, and Vladimir. I'm very happy to present this project with Xiaojuan today. In this project, we focus on photographic image synthesis from semantic layouts. The semantic layout can be as coarse as the left image, or can be as fine as the right one. The image synthesis task is to generate photographic images that conform to the given coarse or fine semantic layouts. As you can see at the bottom, these are two images synthesized by our approach, and they conform to the given semantic layout. At the first glance, they may just look photorealistic. In addition to synthesizing images for street scenes, our approach can also synthesize images for indoor and outdoor scenes. from the NYU and ADE20K datasets. Most recent approaches on image synthesis train deep networks end-to-end. Pix-to-Pix uses conditional generative adversarial networks to perform general image-to-image translation. Cascaded refinement networks, or CRNs, train a deep network with feature losses in a cost-to-find fashion. However, we believe it is highly challenging for a network with limited capacity to model the whole distribution of all natural images. Thus, we explore the ideas of non-parametric models. Let's rewind to a decade ago. There exist non-parametric approaches that use a large image database for image in painting. We believe the process of image synthesis can be facilitated by images retrieved from the database. So a natural question comes to our mind. Can we have the best of both worlds by combining the parametric deep learning and non-parametric database? Here we describe the general idea of our semi-parametric approach. First, we create a database with object segments. We call it external memory. As you can see on the figure, there are sky segments, forest segments, mountain segments, grass segments, and these are extracted from the training set. Then, given a novel semantic layout at the test time, we retrieve compatible object segments from the external memory. Then we merge these retrieved segments onto a canvas. You can see the canvas is incomplete and the overall color distribution may not be natural. Then we refine the canvas with an image synthesis network. Here is our final result. Now, let's go through the technical details. We first construct the external memory with object segments extracted from the training set. Then, given a semantic layout, we retrieve relevant object segments. The next step is to use a transformation network to align the retrieved segments so that the orientations and sizes are consistent with the given semantic layout. Then we paste the transformed segments onto the canvas in an order given by the ordering network. In case that two segments overlap, we need to determine which segment should be occluded by another one. In the next stage, which is the image synthesis stage for the canvas, we refine the canvas with an image synthesis network. The synthesis network takes the semantic layout and the canvas as input. The network architecture of the synthesis network is simply an encoder-decoder. Finally, the network generates the photographic output image. The role of the network here is to harmonize the image, in paint missing regions, and add shadows if needed. Now, Xiaojuan will talk about the results of our approach and comparisons with other methods.
Thank you. We demonstrate our first example on the cityscape dataset with the Kautz semantic layout. Here's the result from Pix-to-Pix and the result generated by CRN. And finally, it is the result that's generated by our approach. All synthesized images are with more realistic structures and textures. Then we demonstrate our second example on the cityscape dataset with the fan layout. Here the result by pix to pix, and the result generated by CRN. And finally, it is the result image generated by our approach. This is another example demonstrated on the GTA5 dataset. The model is trained on the cityscape dataset, and we directly applied the trained model on the novel semantic layout from GTA5 dataset. This is the semantic layout in the GTA5 dataset. Then this is the result from pix to pix. The result generated by CRN. And this is the original image from the GTA5. Finally, it is the image generated by our approach. We believe that someday deep learning may revolutionize how graphic images are rendered. Deep networks could be used to render images directly. Here is an example from the Indao NYU dataset. This is the semantic layout. This is the result produced by pix to pix, result produced by CRN, and finally, this is our generated images. This is another example from the AD20K dataset. AD20K is a challenging dataset that contains diversified patterns for natural things. This is the original semantic layout, result by pix to pix, result by CRN, and finally, this is our synthesized image. Our approach can also synthesize a diverse collection of images. Given a semantic layout, we retrieve different object segments at the stage of canvas generation. Here are 5 images synthesized by our approach. This is another example, the semantic layout. I'll synthesize the results. This is more illustration of semantic layout and the corresponding images generated by our approach. We now analyze the realism of synthesized images in terms of low-level image stats. We consider the mean power spectrum of synthesized images. Compared to real images, the power spectrum for pix to pix has many small specks, while the power spectrum for real images is visually smooth almost everywhere. The power spectrum for CRN has many large specks. In contrast, the power spectrum for our approach is similar to the one for real images. We also conduct perceptual experiments to compare our approach to prior work. We perform A/B tests under 5 experimental settings. At average, in 94% of the comparisons, people believe our synthesized images are more realistic than the ones by pix to pix. And in 86% of the comparisons, people prefer our results over CRN. We have also conducted time-limited pairwise A/B tests. In the experiment, a pair of real image and a synthesized image is shown to a person for a limited amount of time. In less than a second, people have a hard time to tell if our synthesized images are realistic or not. We now saw comparisons with pix-to-pix HD, which is a concurrent work that was shown in the previous talk. These comparison videos will continue to play while we are happy to take questions. Thank you.
That was very nice work. If you've got any questions, please approach one of the microphones. Oh, we got one already. Yes.
Hi. How long does it take to synthesize one image using
Could you get closer to the mic or speak up, please?
My question is about the time. How long does it take to synthesize one image?
Yeah, time is a limitation of non-parametric based approaches. So our approach also has this limitation, but we think everything needs improvement. If we can design more efficient data structures or represent the patches in the feature space, maybe the time can be accelerated. We will do this we will do this to improve this efficiency. Thank you.
So how long is it now? Yeah, just curious.
It's about 3 minutes.
Thank you.
Hi, thank you so much for your presentation. You have really impressive results. I'm wondering if you could comment a little bit on failure cases that you might have observed, because when you're starting from semantic map, it's possible that the network might choose an object that face in the wrong way and things like that. And I'm curious if you have observed anything.
Yeah, I think during the object retrieval stage, sometimes it might have the ambiguity, like the car whether facing the left or right. This is a step I think we can further improve. And here we try a simple approach to avoid picking the wrong object segments. For example, when we retrieve the object segment, we try to have an object segment that have the maximum IOU with the query semantic segment. So in general, we don't have this problem, but in some very few failure case, we observe we may retrieve a card that's not what we want.
Thank you.
All right, let's thank the speakers again.
We will now begin the spotlight part of the session. We ask that when speaker I comes up, speaker I+1 lines up on the right to be ready to come up. So when speaker 1 is up here, speaker 2 should be lined up there. When speaker 2 comes up, speaker 3 should be lined up there. And with that, we will begin.
Hi everyone, I'm Tushar Nagarajan and I'm going to talk about our work Block Drop, Dynamic Inference Paths and Residual Networks. This is joint work with Jung-Woo and Larry Davis from UMD, me and Kristen Grauman from UT Austin, Stephen Rennie from Fuse Machines, and Abhishek Kumar and Rogerio Ferres from IBM Research. Deep residual networks have had tremendous success in computer vision, with popular models earning state-of-the-art results on a variety of tasks. The secret sauce in these models is a residual block, whose properties allow you to stack them repeatedly to form really deep models. While this is great for getting high accuracies on large image datasets, these models come at a high cost during inference time. Previous work has shown that these models are resilient to randomly dropping a few blocks at inference time. Now, while this does save computation, deciding which blocks to drop is not a trivial task. And if you drop too many of the blocks or the wrong sequence of blocks, this often results in incorrect predictions. Our hypothesis is that each image has its own computation requirement. For example, for these images of canonical front-facing dogs, only 8 blocks are really needed to get the correct answer. While for these sneaky dogs disguised as bagels, nearly all of the blocks are needed. Clearly, the characteristics of the image hint at how much computation is needed. Our idea is to capture these characteristics in a model that looks at the image and decides how many blocks to drop, with the goal of minimizing computation without compromising the accuracy of the model. For this, we propose Block Drop, a reinforcement learning-based system that dynamically decides which blocks to drop, given a particular image. It has a policy network that predicts a binary vector U to decide which blocks to drop all at once. So in this binary vector, a 1 means keep the block and a 0 means drop it. The network is rewarded based on 2 things: how correct the model is and how many blocks it managed to drop. So if the model correctly predicts that the image is a dog, then a positive reward is given. And the more blocks you drop, the higher this reward. If it gets it wrong, though, then a negative reward is given, regardless of how many blocks are dropped. The combination of these two rewards forces the model to learn configurations that minimize the amount of blocks used, as well as produce the correct answer. Overall, our model has two parts that work in concert: a ResNet for image classification and a policy network to drop the blocks. The model is trained with policy gradient, and the ResNet is also fine-tuned concurrently. Compared to a ResNet that uses all of the blocks, our model uses 20 to 36% fewer flops. If you're running an API service that handles 1 billion requests per day, this translates to 1,000 hours of computational savings. In addition, because of the way we're dropping blocks during training, it acts as a regularizer, allowing us to get higher accuracy using fewer blocks. We also outperform other state-of-the-art conditional computation models for the same task. We also noticed that the configurations of blocks predicted by our model encodes visual patterns. For example, images of groups of oranges tend to be assigned the second and third block of the ResNet, whereas images of sliced oranges tend to be assigned a completely different configuration of blocks. Finally, our model is able to automatically discover the difference between easy and difficult instances and allocate an appropriate amount of computation for each of them. This agrees well with our notion of instance difficulty. Please stop by our poster for more information. Thank you.
Hello, everyone. I will introduce the Interpretable Convolutional Neural Network. This study is done by Zhang, Ming-Yu, and Song-Chun. We have released code in the GitHub. University of California, Los Angeles, and Shanghai Jiao Tong University. In previous study, traditional neural network, a filter usually represents a mixture of texture and paths. For example, a single filter may be triggered by different paths. You can see this is an example. This filter is triggered by 3 different paths on the dark. So in our study, we aim to learn an interpretable convolutional neural network, where each filter represents a single path among different objects. We do not use any annotation of paths or textures for supervision. We automatically learn such a path repetition from the raw data. So the input is the same, exactly same as the traditional neural network. We can collect training sample for classification or segmentation. We do not label any paths or texture. So we add a certain loss, named filter loss, to each feature map of our filter. The filter loss is formulated as a minus mutual information between the given feature map and a number of predefined template. So the filter loss encourages a low interclass entropy. That means each filter should only be triggered by a single class instead of multiple classes. And this filter loss can also encourage a low spatial entropy of the neural activation. That means in each feature map, the filter should only be activated in a single unit, in a single location, instead of having 3 or 4 peaks. We assume that texture patterns always have several peaks in the feature map. But if this feature map represents a path, it's always single peak. These slides show our result. You can see each filter represents a certain object path among different objects. They usually detect the hand pattern because maybe it's because the hand is the most discriminative. We can apply our method to different models, including XNet, VG16, VGM, and S. And theoretically, we can apply our method to different tasks. We also propose a new evaluation metric for object path interpretability. That's the location instability of filters. We assume that if a filter represents a path, then the relative distance between the inferred position and some ground truth landmark should keep stable through different images. So our method shows much higher interpretability. That's much lower location instability than traditional neural network. And in particular, for multi-class classification, our method outperforms traditional convolutional neural network. So in conclusion, we propose a simple yet effective method to modify traditional convolutional neural network into an interpretable convolutional neural network. Each filter in a high convolution layer represents an object part. We do not need any annotation or part or texture for supervision, and we can apply our method to different tasks or different scene structures. We have released our code in the GitHub. Thank you very much. Welcome to our poster F7.
Hello, everyone. Very glad to present our work here, Deep Cross-Media Knowledge Transfer. The authors are Xin Huang and Professor Yu Xinpeng. We are from Peking University. The topic of this paper is cross-media retrieval, which aims to perform retrieval across different media types. For example, by an image query of Golden Gate Bridge, the system can return relevant data of image, text, video, audio, and 3D model. The key problem of cross-media retrieval is that different media types have inconsistent representations, so their similarity cannot be directly computed. The current mainstream methods are to use deep learning for generating cross-media common representation, so the cross-media similarity can be computed. Existing methods face the challenge of insufficient labeled cross-media data. The retrieval accuracy usually relies on the amount of training data. However, it is extremely label-consuming to label cross-media data. Imagine you are labeling the data of Golden Gate Bridge. You have to see the image, read text, watch video, listen to audio, and even observe 3D model. This limits the performance of current cross-media retrieval methods. Transfer learning is usually used to relieve the problem of insufficient training data. However, existing transfer methods are mostly designed within the same media type. They pay little attention to knowledge transfer between two cross-media domains, including intermediate semantic and intermediate correlation knowledge. Therefore, we propose deep cross-media knowledge transfer, DCKT method, to transfer from cross-media source to target domains. This is the overall architecture of DCKT, which has two transfer levels. First, media level transfer is proposed to transfer intermediate knowledge between two domains with MMD laws and pairwise laws. Second, correlation level transfer is proposed to align intermediate correlation of the two domains, including MMD laws and semantic laws. In this way, knowledge in source domain can be jointly transferred to target domain for boosting retrieval accuracy. Cross-media domain gap is very vast, and hard transfer samples lead to negative transfer effect. We further propose progressive transfer mechanism. We let the model pre-trained in source domain serve as a teacher. Then we automatically select samples in target domain during transfer process. In this way, we gradually transfer from easy to hard samples for robust training and higher retrieval accuracy. Next experiment. The self-constructed X-media net dataset is used at the source domain, which is a large-scale dataset with more than 100,000 instances. We adopt 3 widely used but small-scale datasets as a target domain. Compared with the methods which are only trained with the target domain, DCKT can obtain inspiring improvement of accuracy. Thank you for listening. Here are the QR codes of our lab homepage and GitHub homepage. Welcome to our website for more information. Thank you again.
Hi everyone, I'm Ting-Chun, and I'm going to present our work named Interleaved Structured Space Convolutional Neural Networks. This is a joint work done with Guo Tianxie, Jingdong Wang, Jianhuang Nai, Ri Changhong, and Guo Junqi. Deep convolutional neural networks with small model size, low computation cost, but still high accuracy become an urgent request. Most existing technologies focus on designing efficient and effective convolutional tuners. We roughly divide them into 5 categories. They are low precision tuners, low rank tuners, composition from low rank tuners, sparse tuners, and composition from sparse tuners. Our work belongs to the last category, using the product of sparse tuners for composing a tuner. Recently developed algorithms such as interleaved group convolutions, deep roots, exception, shufflenet, and mobilenet compose a dense tuner using the product of 2 structured sparse tuners. We observe that one of the 2 tuners can be further approximated. For example, the suggested secondary group convolution in interleaved group convolutions contains 2 branches, and each branch is a 1-by-1 convolution, which can be further approximated. Motivated by this observation, we designed a building block, IGC version 2, which is interleaved structured sparse convolution. The main idea is to further decompose the dense convolution in IGC version 1 by multiplying sparse matrices, thus further eliminate the redundancy and saving the storage and the time cost. Such process can be repeated multiple times, resulting in successive group convolutions. In our design, we separate the convolution along the spatial domain and the channel domain. That is 1 channel-wise 3-by-3 convolution and L-1 group 1-by-1 convolutions. We also introduce the complementary condition and the balance condition. The complementary condition guarantees that each output channel is connected to all the input channels so that the resulting convolution tuner is dense. The goal of balance condition is to have the smallest number of parameters so that there is a good balance among 3 aspects: model size, computation complexity, and classification performance. Here we show experimental comparison to IGC version 1 and MobileNet version 1. The first row shows the comparison to IGC version 1 on CVPR100. Our proposed IGC version 2 shows superior results with fewer parameters and less computation complexity. The second row shows the comparison to MobileNet version 1 on ImageNet. It can be seen that the performance gain is larger when the model becomes smaller. We further extend IGC version 2 by combining the structured sparse matrices with low-rank matrices. Here we show some preliminary results. The left table shows the comparison to MobileNet version 2 on ImageNet. We can see that IGC version 3 shows better performance on the small models. The right table shows the total object detection results, showing IGC version 3 achieves comparable performance with few parameters. To conclude, we introduced a new building block called IGC version 2, which enjoys the benefits of small model, fast computation, and high accuracy. Our code is available at GitHub. For more details, please come to our poster at booth F11. Thanks for your attention.
Hi, I'm Patrick Esser from Heidelberg University, and I will present a variational unit for conditional appearance and shape generation. This is joint work with Ekaterina Suter and Björn Ommer. To generate images with neural networks, we usually transform some low-dimensional input through a generator into some high-dimensional image displays. Now, of course, generating just a single image usually poses no difficulties. However, we want to be able to generate all kinds of naturally occurring images. To tackle this problem, we should utilize some of the structure provided by natural images. The idea is to differentiate between image variations caused by 2 very distinct factors. In the vertical direction, we can see changes in appearance, such as textures, colors, or identities. The horizontal direction shows changes in pose or viewpoint, simply referred to as shape. Now, it's important to disentangle those two factors because their behavior is actually quite different. Considering changes in appearance, these changes can actually be explained quite well by a simple linear interpolation of images. On the other hand, considering changes in shape, the same description completely fails to capture the nature of these changes. In this case, the interpolated images are not natural images anymore. Therefore, a generative model which tries to explain all image variations in the same way cannot work. To model changes in shape, we therefore add a shape estimator to our model and utilize skip connections to propagate spatial informations to our generator. To disentangle shape and appearance, we penalize redundancies between the representations. As a result, not only can we produce high-quality images, but we can also produce variations in shape and also in appearance. Due to the disentangled representation, we actually can control both factors independently, which gives us complete control over generated shape and appearance. In experiments, we show that our method does not depend on a specific shape estimate, which makes it applicable on a wide range of objects. Furthermore, we evaluate its ability to transfer shape and appearance between given images, as well as to sample new appearances. Both qualitative and quantitative comparisons show significant improvements over previous methods. Finally, our model is able to produce videos from a single static image. If you would like to know more, please visit us during the poster session or take a look at the results and code provided online. Thank you very much for your attention.
Hello everyone, I'm Chen and she is Yun from National Taiwan University. Today we will present our works, Detach and Adapt, Learning Cross-Domain Distangle Derepresentation. So human beings have the ability to extract specific features from data. For example, when we see this summer scenes image, we can imagine the same scenes in different seasons, such as winter or fall. This is achieved by disentangling the season's features from image. Recent works attempt to fulfill this ability with a learned generator. By manipulating the interpretable factor, one can generate the image with attribute of interest. Moreover, human beings have another ability. For example, we can extract seasons from photos, and then we are able to transfer disentangleability from photo to painting without additional supervision. Similarly, we are able to disentangle factual expression from photos and transfer to cartoon without additional supervision. So, how about machines? Therefore, we aim to fulfill cross-domain representation disentanglements on machines. To be more detailed, our goal is to design a unified framework for cross-domain representation disentanglement with the supervision from single domains. So basically, our proposed model is based on GAN. We aim to learn the disentangle representation by maximizing the mutual information between disentangle factors and synthesized image. And the ground truth information is only available in source domain. So the semantics of the angle factor is learned from source domain data. To further address domain shift, we share both generator and discriminator. We further add additional encoder to perform the image translation condition on attribute of interest.
In our experiment, we have 3 different tasks, including cross-domain image synthesis, cross-domain image translation, and unsupervised domain adaptation. In cross-domain image synthesis, we first disentangle smile attribute from photo domain and transfer this ability to sketch domain even without any supervision. Similarly, we can transfer this ability to multiple target domains in different digit datasets. In cross-domain image translation, given input images, we first manipulate glasses attribute of facial images in sketch and photo domain, respectively. Then we can translate the disentanglement ability to another domain. That is, we can perform image-to-image translation and manipulate attribute of interest at the same time. Similarly, in the case of sync images, we can do image-to-image translation between photo and painting domains and manipulate day or night attributes simultaneously. Finally, in unsupervised domain adaptation, we achieve satisfactory results in digit, phase, and sync datasets. We also observe that the features are separated to 10 classes, and the features of source and target domain are aligned together. If you are interested in our work, please come to our poster session at F15. Thank you for your attention.
Sorry, I'm Diego Marcos from Wageningen University, and I'll be presenting some work I've been doing with Davis Tuya, also there, and the team of Raquel Urtasun in Toronto. So I'll be talking about image segmentation applied to instances of buildings in remote sensing images. So in this case, geometry plays a particularly big role because the result is supposed to be a polygon that contains straight lines and edges. Sorry. But so if we were in the 90s, probably we would think of applying models of the family of active contour models, where basically we start with an initialization that would look like the yellow circle, and then we design an energy that will try to maximize the amount of this contour that is on top of edges. The result that we would obtain out of this would probably not be what we want, and therefore these kind of old models added some additional terms that regularize the result, like imposing some priors that we have on these shapes, like we want the result to be short and to be smooth. This would, again, bring some problems, like making the result too small, and therefore other terms can be added that inflate this by maximizing the surface that is covered by these contours. Then the problem with this sort of model is that the different terms need to be tuned to find a good balance between over-smoothing and the problem that we see now, that will be overfitting the little spurious edges. If we come back to the future, we would probably think of solving this problem with CNNs, which can do like a really good job at this, but that are don't allow to very easily encode for certain priors that we already have. So we were thinking about trying to bring the good things of these two families of models, so like the powerful feature extraction capabilities of CNNs, and also the capability of easily applying priors that active contours give. For this, we will use a CNN that can give us the parameterization of the energy function of active contour models. And as we can see in this result, the CNN has been able to learn edge detector that is specific to buildings. It has been able to learn to penalize the curvature only in the edges and not in the corners. And well, if you want to know more about this, how we learned this just with polygonal ground truths and some nice results on the Toronto City dataset, please come to the poster at F17. Thank you.
Hello, my name is John Lambert, and this is joint work with Ozan Sainer and Silvio Safarese. And this work combines deep learning with the learning under privileged information loopy paradigm. So this models a scenario where at training time we have additional information that is absent at test time. And we compare this scenario to learning with an intelligent teacher in training. And the word heteroscedastic in the title means a varying variance. So suppose we have tuples composed of an input x, privileged information x star, and a label y. Privileged information arises naturally. For example, in image classification, the tuple might consist of an image, a bounding box, and a class name. For machine translation, the tuple might consist of a German language sentence, an image depicting the scene described in natural language, and the label might be the English language translation. In this work, we question what is the correct way to provide auxiliary information to a network. The first equation describes what many have done, where we only use XY tuples and ignore the privileged information, which is quite wasteful. The second equation here is unsuitable. Always using the privileged information as a rigid model input will fail since we don't have it at test time. Our main idea is to use the privileged information as an input, along with a multi-view hypothesis class, specifically with two views of the data. One view, H naught, shown on top, accepts X, another view, H star, shown at the bottom, accepts X star. We follow Bayesian learning, and our network makes a Bayes optimal decision at test time via marginalization over the distribution of privileged information. Similar to Bernoulli dropout, our dropout is multiplicative via the Hadamard product, but we draw samples from a different distribution, namely a Gaussian. And via the reparameterization trick, we can make our dropouts noise a function of privileged information. Thus, it is heteroscedastic because the samples come from a distribution with a varying variance. So in practice, for a CNN, one way to accomplish this goal is to use two towers. At test time, our marginalization can be achieved via an architectural specification. We will only use the top tower at test time. In a recurrent neural network, one implementation is to utilize Gaussian dropout between the layers. To test the CNN's sample efficiency, we train models on increasingly large subsets of ImageNet. In the next slide, we show a log-log plot of accuracy versus training set size. Our key result is shown here in blue. In a small data regime, we can learn a similar accuracy with 25,000 fewer training samples when compared with a model that ignores site information shown in green. With a large training set size, our performance is identical. The intuition is that with enough examples, one does not need a good teacher because we can simply learn by brute force. In the next slide, we show the results of models trained on a 75,000 image subset of ImageNet. In light blue, we show those models trained without privileged information. In green, we show previous approaches for loopy with deep learning, and in red, we show our result. Put simply, privileged information can provide a 5% top 1 accuracy boost on this task with the same training set size in a small data set regime. Thus, our method is a way to improve sample efficiency. In an analysis of the algorithm, we rigorously prove that it is possible to learn an order of magnitude faster with privileged information in the Oracle case. For theoretical details, please come to our poster at F19. Thank you very much.
Hello everyone, I'm Yuchen Luo from Tsinghua University. Today I will introduce smooth neighbors on teacher graphs for semi-structured learning. As collecting a fully labeled dataset is often very expensive and time-consuming, we want to use a large amount of unlabeled data to improve the generalization performance. More recently, due to the great advances of deep learning, deep semi-structured learning achieves remarkable results. One is the combination with deep generative models such as VAEs and GANs. Another is the perturbation-based approaches, which explores the idea that classifiers need to be invariant to local perturbations along the data manifold, such as PAN model, temporal ensembling, and the mean teacher. They define a consistency loss that encourages invariant predictions between a teacher model F turtle and a student model F under some perturbations. The teacher is usually a self-ensembling of student models, which is a little better than the student. However, this method only consider perturbing each single data point, while ignores the connection between data points, therefore not fully utilizing the information in the unlabeled data structure, such as clusters and manifolds. We address it by proposing a new method, SNTG, that enforces the predictions of neighbors to be smooth, which is a stronger regularization than only imposing smoothness at each single unlabeled data point. We built a graph representing the similarity between data points using the predictions given by the teacher model. Then we encouraged the features of neighbors on this graph to be close and the non-neighbors to be separated at least a margin. The method is simple but effective, which can be applied to existing semi-supervised method without additional training time. Now, let's look at some experiment results. First, we achieved state-of-the-art performances in semi-supervised classification on benchmark datasets such as MNIST, SVHN, and CVPR18 compared to strong baselines, including generative models and perturbation-based methods. Second, when the labeled training data points are very few, we can see that SNTG has better generalization performance on MNIST with only 20 labels, also on the CVPR18 dataset with only 1,000 labels. In addition to the benefits from partially labeled data, SNTG also can learn from noisy supervision. Adding our method shows almost perfect robustness even when 90% of the training labels are corrupted. Next is the visualization of feature embeddings. As shown in figure B and D, our method helps to form tighter and more concentrated clusters for each class, which is consistent with our assumption. Finally, SNTG is general and can be combined with generative models. We observe that our method can not only reduce the error rate of the improved GAN, but also improve the generalization quality and diversity. For more details, please come to our poster at F21. Our source code is also uploaded to GitHub. Thank you.
Good afternoon, everyone. My name is Wang, and I'm from Tsinghua University. Today, I'm excited to share our work on the interpretability of deep neural networks. In this work, we propose a flexible framework to interpret a deep neural network by identifying critical data routing paths. Interpretability of deep neural network aims to explain the rationale behind its decisions and enable the users to understand the intelligent agents. it becomes an important issue in the task-critical applications, such as medical diagnosis and self-driving cars. In this work, we introduce a new perspective on interpreting neural network behavior by identifying the critical data routing paths of each given input. Specifically, we consider routing paths are composed of critical nodes on each layer, and we denote the critical nodes on the routing paths as the important channels of intermediate layers output that if they were suppressed to zeros, the final test performance would deteriorate severely. To efficiently discover the CDRPS, we developed a distillation-guided routing method. Inspired by channel pruning and knowledge distillation, we associate a scalar control gate to each layer's output channel to learn the optimal routing path for each individual sample. The optimization objective is to ensure that the subnetwork outlined by the CDRPS preserves the knowledge of the original model. The final identified CDRPS can be represented by concatenating the optimized control gates from all layers, which can be regarded as a new form of activations. In the experiments, we observed that CDRPS representation can reflect the input layout patterns. The red figure shows that interclass sample clustering result based on the whole CDRPS representation correspond to input layout patterns strongly. Human evaluation also confirms CDRPS capture better sample similarity than baseline methods. We also discovered that the CDRPS of adversarial images diverge from those of the real images and follow similar routing paths with those of target class images. However, the divergence is not obvious when the adversarial target class is much semantically closer to the real image class. Therefore, based on the above observations, we propose a novel adversarial sample detection scheme by training a binary classifier to discriminate whether the CDRPS are from real samples or adversarial samples. Experiments shows that our method achieves higher defense success rate with less computation overhead, and the adversarial attacking can be defended based on the CDRPS representation. In conclusion, we investigate the topic of neural network interpretability from a new perspective by identifying the critical data routing path. We propose a distillation-guided routing method, which is a flexible and general framework to efficiently learn the control gates. We found semantic concept contained in the CDRPS. Specifically, the whole CDRPS reflect input samples layout patterns. Finally, we propose a novel adversarial sample detection method based on the discrimination on CDRPS of real and adversarial images. Welcome to discuss at a poster session, and thank you for your attention.
Good afternoon. My name is Iasonas Kokinos, and I will be presenting work by Siddharth Chandra and Camille Coubré done during Siddharth's internship in FAIR Paris. If we perform frame-by-frame segmentation with Mascar CNN, we see that by ignoring temporal context, the method occasionally makes false detections, misses some objects, and does not have smooth predictions. By contrast, the method that we will describe here, called Video Gaussian CRF, exploits temporal context, allows information to flow across frames, and has smooth and consistent predictions in time. Our approach is versatile and allows us to address semantic segmentation, instance segmentation, and instance trunking in the context of video. It's particularly efficient and allows us to perform inference with CRFs in video. So considering a single video frame and its partition to a set of patches, fully convolutional neural networks treat each patch independently, so the predictions are not coupled among themselves. So several spatial CRF methods use graphical models where each node is connected to its immediate neighbors via pairwise terms. Densely connected random fields allow every node to see all other nodes in the same image, so they can easily flow information in space. And we can also extend this trivially in time by doing a densely connected inference per frame. However, this does not exploit temporal correlations. Instead, what we propose is to have fully connected networks both in space and time, in which case every neuron looks at all other neurons in the same video. So this can be computationally challenging. So for this, we need to make a particular choice for the CRF. We rely on the Gaussian random field idea, which has a quadratic form for the energy, which can then be very efficiently solved by solving a system of linear equations. So in this work, we make a particular choice for the system matrix A. We set it to be low rank, which amounts to forming its elements in terms of the inner products of learnable embeddings. To get a feel of what these embeddings reflect, we're showing here for the cross shown on the top frame, its affinities with all other pixels in space and in time. And these are used to perform inference on the whole video. And we see that this allows us to remove the spurious camel in the middle column by jointly reasoning both in space and time. So that's for the case of instance segmentation. I should note that these embeddings are learned by backpropagation, since we can backpropagate through the linear system equation. So in recap, our system builds on a standard fully convolutional network that has local predictions. It's extending this, as is common in many other works, with spatial terms, computing terms of embeddings, such as the densely connected Gaussian random field. But what is new here is that we also exploit temporal information in terms of a learnable temporal embedding that allows us to couple neurons both in space and in time. So the joint system formed with this learned coupling allows us to form the Gaussian random field, which diffuses information both in space and in time. So compare here a baseline with our proposed method. We see that we have much less flickering, for instance, on the pavement. We don't misclassify the bus with the wall, as our baseline does, and we're overall much more consistent and reliable in our prediction. So this is for video semantic segmentation. We have shown that this can be used in many other tasks. Maybe the most exciting is that we can use this halfway in the network, so for instance segmentation. So here we have two frames. We couple them halfway before Roy pooling, and this allows us to diffuse information both in space and time. This is what gave us the results I was showing in the beginning of this presentation. This is because the method is extremely efficient. It just relies on a linear system solution. So we have state-of-the-art results in 3 video segmentation tasks, and we can see much more of those at my poster. Thanks.
Hi, my name is Andrew Shin from the University of Tokyo, and I'm going to talk about customized image narrative generation via interactive visual question generation and answering. And I also worked with Yoshitaka Oshiku and Professor Tatsuya Harada. So in image description task, we usually assume that there's a set of ground truths that are universally applicable regardless of the target or scope of the description. For example, given these two images, a description would be considered correct if it talks about the general aspects of the marketplace or the club. But if you have a knowledge that the target viewer is interested in watermelons or interested in females, then a better description for this particular user would be something like this. So we want to learn the user's interest and customize the description according to it. So the question is, how do we learn the user's interest? Obviously, we didn't develop a model to read the user's mind, and we do it instead by asking questions directly to the users. But not any type of question is viable for learning the user's interest. We need questions that have multiple possible answers so that user's answer can reflect the user's unique attention and interest. For example, in this image, an answer to the question, what is the weather like, will most likely be cloudy, whereas a question like, where is this, might lead to different answers, like outside, train station, or forest, from different people, depending on what they focus on. However, previous question generation models do not take this into consideration. So in order to generate questions with multiple possible answers, we internally run a self-Q&A model where we generate the questions and look at the probability distribution for the answer candidates for the question. And if the probability for the most likely answer is greater than a threshold, then the question is considered to have a single obvious answer, and it gets filtered out because it's likely to have only one answer and cannot reflect the user's unique attention. On the other hand, if the probabilities for the answer candidates are more evenly distributed, then the question is considered to have multiple possible answers. So the question is asked to the users, and the users get to provide their answers to the questions depending on their attention. And the corresponding region to the answer is extracted, and the image description task can proceed. So now that we have an input from the user, we can incorporate it in the learning process as a feature to be embedded along with the image and the question, and apply the resulting choice factor to a new image and a new question so that we can predict the answer that the user is likely to provide upon the question, and then proceed with the image description task that better reflects the user's interest. For this learning task, we collected actual human responses to the generated questions from 3,000 users on Mechanical Turk. So when it's applied to the same image as the one that the question is generated from, given an image like this and a question like this, different people provide different answers, and we generate different descriptions from the regions that are most likely to reflect their answers. And when it's applied to a new image and a new question, people again provide different answers, and we generate different descriptions from new image that are most likely to reflect their interest. Thank you very much, and come see our poster at G5. Thank you.
So that concludes our session. Let's have another round of applause for all the speakers.